Hello again, everyone. So like she said, I'm going to talk about IBM Watson and cognitive computing. Talk isn't going to be very technical. And just a little bit of background. I've only been with IBM for 3 months, so I started in January. And my role is a software engineer. Like I said earlier, I do more data science. I'm working on prognostic models for healthcare. And I'll get more into that in a little bit. So there have been 3 eras of computers. Tabulation, which was the basic form of computers, electronic computations, punch cards, paper reports, and then programmatic, which is kind of what we all know and use every day. They're deterministic, machine language, simple outputs. Most digitized information of the past has been structured information, and that's meaning it was organized into tables that is stored in easily identified cells in databases that can be searched. So if you have a table that has names and birthdays, you say, what's Samantha's birthday? It finds my name. It knows the next column is my birthday. Simple outputs. Unstructured information has largely been ignored because it's difficult to utilize, and traditional IT has limited itself to deterministic applications. So like I said before, the birthdays, 2 plus 2 is 4, 100 centimeters in a meter, that sort of thing. Situations where there's only one answer to a question is what programmatic is. This rules out a lot of real-world situations that have more probabilistic outcomes. It's, so example, it's unlikely, or it's very likely that a car will not start because of a dead battery. However, it might not be starting because of a clog in the fuel line. So traditional IT relies on search to find the location of a key phrase. Emerging IT gathers information and combines it for true discovery. So that's what Watson does with cognitive computing. It's discovery, it's probabilistic, it handles big data, and it uses natural language. So the problem of big data is more than just volume. There's terabytes to exabytes of existing data to process, but there's also velocity, streaming data. For example, there's 17 terabytes of tweets per day and 60 hours of video uploaded to YouTube per minute. There's also lots of variety, like I talked about structured and unstructured data. There's tons of unstructured data. And then veracity. So there's uncertainties. There's inconsistencies, ambiguities. You don't know if the data is relevant or not. Maybe it'll be useful, maybe it won't be. So what Watson is and isn't. So Watson is not a search engine. It's not a massive database lookup. And it's not a strong artificial intelligence of science fiction. What it is a massively parallel probabilistic, evidence-based question and answering engine. It relies primarily on unstructured text analytics, so statistical natural language processing, and it uses unstructured, semi-structured, and structured sources. The structured sources provide a background for interpreting the unstructured text, and the focus is on the natural language processing. Okay, so the difference between search versus Watson. So if a decision maker has a question, they usually pick out 2 to 3 keywords, and then they go to a search engine such as Google, search. The search engine finds documents containing those keywords and delivers them based on popularity. You get those results, you read the documents, find the answers you're looking for, and you yourself finds and analyzes the evidence. So with Watson, the decision maker can ask a natural language question, give it to Watson, who can understand the question in natural language, produce possible answers and evidence, analyze that evidence and compute confidence, and then deliver you the response, the evidence, and the confidence. So you have to do less work. So there's some common myths about Watson. One is that Watson answers a question by translating the natural language into a formal structured query and issue it against a database of accumulated knowledge. That's the approach of standard QA systems and something that like Wolfram Alpha uses. However, Watson relies on unstructured text analytics. Another myth is that Watson identifies the question answer type, for example, president, country, location, date, and then generates candidates from precompiled lists of type instances. This is, again, a traditional QA approach, but Watson uses an open domain coercion technique to generate candidate first and then check type match later. And lastly, another myth is that Watson only uses either unstructured or structured data, when actually it integrates the analysis of both unstructured and structured data. So, one of the things about cognitive computing is understanding why it's hard for computers to understand humans. For example, noses that run and feet that smell, ship by truck and send cargo by ship. How can a slim chance and a fat chance be the same while a wise man and a wise guy are opposites? How can a house burn up as it burns down? Why do we fill in a form by filling it out? And how does an alarm go off by going on? So, so much of the difficulty is rooted in the fact that computers speak a different language than humans. Computers handle precise numbers, and everything they do is built on this capability. People handle words and ideas with different meanings. It all depends on context of what you're saying. So this is an example. So in the table there, like I said earlier, you say person, J. Welch, you go to organization, GE. That's a typical computer works. However, Watson can understand that if it's given something like the example on the right there, if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. That's something that Watson can understand, and using that and maybe some other things can answer the question, the Jeopardy type question, Welch ran this. As to where if it's looking just at structured data, it's probably not going to get that being able to find Welch and then GE. Okay, so I'll go over a little bit of deep QA, which is IBM's algorithm or architecture, I guess is what they call it, behind Watson and the process Watson goes through to deliver you your answer. This is, like I said before, Watson was developed to play Jeopardy, and this is kind of what they call it is the brain of the Watson system from 30,000 feet above. It's just a high-level overview. So each component in the system adds assumptions about what the question might mean, or what the context means, or what the answer might be, and why it might be correct. Over 100 different algorithms are implemented as components. So there's a lot of algorithms. Okay. The first step is the question and category analysis. It parses algorithms. Parsing algorithms decompose the question into its grammatical components, and other algorithms here will identify and tag specific semantic entities like names, places, or dates. In particular, the type of thing being asked for, if it is indicated at all, will be identified. We call this lexical answer type. Categories in this are like fish, character, country. Next is query decomposition, where different assumptions are made about if and how the question might be decomposed into sub-questions. The original and each identified subpart follow parallel paths through the system. Next is hypothesis generation. And Deep QA does a variety of very broad searches for each of several interpretations of the question. Watson, to compete on Jeopardy, is not connected to the internet, so it's not doing an internet search. So these searches are performed over a combination of unstructured data, natural language documents, and structured data that are in available databases and knowledge bases that were fed to Watson during training. So all the knowledge Watson has is, it's been read into it. It's been trained on that data. The goal of this step is to generate possible answers to the question and its subparts. At this point, very little confidence is in these possible answers, and little intelligence has been applied to understanding the context that might relate to the question. The focus at this point is on generating a broad set of hypotheses, or for this application, we call them candidate answers. And to implement this step for Watson, we integrate and advance multiple open source text search components. After candidate generation, Deep QA also performs soft filtering, where it makes parameterized judgments about which and how many candidate answers are most likely worth investigating, more computation given specific constraints on time and available hardware. Based on trained threshold for optimizing the trade-off between accuracy and speed, self-filtering uses different lightweight algorithms to judge which candidates are worth gathering evidence for and which should get less attention and continue through the computation as is. In contrast, if this were a hard filter, those candidates falling below the threshold would be eliminated from consideration entirely at this point. So next, in hypothesis and evidence scoring, the candidate answers are first scored independently of additional evidence by deeper analysis algorithms. This may, for example, include typing algorithms. These are algorithms that produce a score indicating how likely it is that a candidate answer is an instance of the lexical answer type determined in the first step. For example, country, agent, character, city, book, etc. Many of these algorithms may fire using different resources and techniques to come up with a score. What is the likelihood that Washington, for example, refers to general, capital, state, mountain, father, or a founder? For each candidate answer, many pieces of additional evidence are searched for. Each of these pieces are subjected to more algorithms that deeply analyze the evidentiary passages and score the likelihood that the passage supports or refutes the correctness of the candidate answer. These algorithms may consider variations in grammatical structure, word usage, and meaning. In the synthesis step, if the question had been decomposed into some parts, one or more synthesis algorithms will fire. They will apply methods for inferring a coherent final answer for the constituent elements derived from the subparts. And finally, arriving at the last step, final merging and ranking. There are many possible answers, each paired with many pieces of evidence, and each of these scored by many algorithms to produce hundreds of feature scores, all giving some evidence for the correctness of each candidate answer. So the answer with the strongest confidence would be Watson's final answer. And Watson would try to buzz in provided that the top answer's confidence was above a certain threshold that was picked. All right, so that's a high-level overview. I don't know the technical details all that much in it because that's not my specific area. But, okay, so this is something that would look like. It's given this. In 1698, this comet discoverer took a ship called the Paramore Pink on the first purely scientific sea voyage. So that's fed into Watson. Question analysis, it picks out the keywords, the date, 1698, comet, Paramore Pink, the answer type, comet discoverer, the date, took, called. That's how it breaks down the question analysis. Then it goes through the primary search, related content, structured and unstructured, all the knowledge that Watson has. Comes up with possible answers, large list. Goes through the filtering, evidence scoring, and finally it will give you its most likely answers and its confidence in them. So competing on Jeopardy, it's got an 85% confidence that Edmund Halley is the correct answer. It's going to buzz in and give that answer. Okay, so this is another look at kind of the breakdown on how Watson picks things out. So it can go through and pick out the symptoms. It'll go out through some. This is just a medical journal article. It can go through and pick out the diseases, the medications, and then the modifiers. So it can break down anything it reads into that. So now I'm going to talk a little bit about Jeopardy and the math, some of the math concepts that went into it. So the goal to build a simulation model of the domain using historical contestant data. So it was fed in historical questions, answers, all that stuff. They applied machine learning and optimization techniques with simulation to develop Watson's strategies. So for the daily double betting, they used neural nets for fitting nonlinear models and reinforcement learning. The final Jeopardy betting was a best response game theory. The clue selection, daily double seeking Bayesian inference. And for the confidence threshold for buzz-in, approximate dynamic programming and real-time rollouts. So those are just high-level overviews of some of the math that goes into the actual algorithms in Watson. This chart just shows, over time, the incremental progress made and the trade-off between precision and percent answered. And percent answered is kind of related to the confidence, how confident Watson is in its answer. So down here was the baseline where they started in December of 2006. And then with each line, they move all the way out there to the plane in the winner's cloud in, November of 2010. And Watson was on Jeopardy! I believe February of 2011. So now Watson has moved beyond Jeopardy, but it's a non-trivial challenge. So on the left here, this is some of the Watson statistics or information from Jeopardy! There was one user, max input was 2 sentences. It took 5+ days to retrain Watson if it needed more data or new evidence. The evidence was not present. So it didn't give you any reason why it chose this answer. There was no evidence there. Text-only input, so you had to, I think when it was on Jeopardy, they typed in the questions to it. It's a QA model and just basic security. Now, Watson, there's tens of thousands of concurrent users. Everyone in IBM that's working on Watson can log in, access it. There's pages and pages of input. I don't know the exact numbers, but Watson can read in like billions of documents in 5 seconds. It's ridiculous the amount of information it can read in. Dynamic content ingestion, so it can constantly be updating itself and getting new information. Supporting evidence, we now do have supporting evidence. If a doctor, for the healthcare example, if a doctor looks up and wants a treatment plan, it will give him evidence as to why it's giving him this treatment plan. It can be text, tables, images as input, natural language. A doctor can write a sticky note and says, patient A has symptoms, headache. And Watson can read that in. It can scan it and read in that handwriting. It's both a Q&A and conversation model. And now we have high security. We're working with medical records, so it's secured. It has to follow all the HIPAA standards. So understanding where to put Watson to work requires an understanding of where to apply cognitive capabilities. So the difference is Watson uses deep analysis of language, unstructured content navigation, decisions using disparate data sources, learning based on historical and ongoing cases, and iterative case analysis. So these are different than traditional approaches. Traditional approaches just require numerical analysis, direct information retrieval, correlation of large data sets, predictive analysis, or computing an unknown answer. Okay. So Watson brings together transformational technologies to drive optimized outcomes. Like I said many times, it understands natural language. It can adapt and learn, and it generates and evaluates hypothesis-based evidence-based hypothesis. All right, there's 4 main industries IBM is focusing Watson. The major one is healthcare. We have several healthcare clients, and that's where our focus has been. But we are branching out into financial services, call centers, and also some government sectors. So I'm going to talk about the healthcare because that's what I'm working in and that's what I'm most familiar with. And the goal for IBM is for cognitive computing to transform healthcare, to engage patients, improve outcomes, and control costs. These are just some of the products that we have, like some of our solutions for healthcare. I'll talk a little more about a couple of them, but it's basically transform interactions and experiences with consumers, members, and patients. Okay, so the way Watson is changing medicine, we're working with MD Anderson, connecting clinicians and researchers. We're changing the way it's taught through students learning at the Cleveland Clinic, the way it's practiced with the cancer centers at Memorial Sloan Kettering, and the way people pay for medicine with WellPoint and its utilization management. So those are our 4 main partners. So first, the Cleveland Clinic. The project here is Watson Paths and Watson Electronical Medical Record Assistant Research Projects. So the business problem is medical students and doctors easier insight into the data to inform their diagnosis and decisions. And our solution is intuitive new user interface to Watson's power-revealing chains of evidence to support clinical reasoning and analysis of whole electronic medical records to extract and visually represent summarized knowledge with semantic understanding of context. We're also applying Watson to oncology, and cancer is the cause of 1 in 4 deaths in the United States. So these two are WellPoint's interactive care insights for oncology, and that's with Memorial Sloan Kettering as well. And they need a better individualized cancer treatments. Not everyone's cancer is the same. The goal is to individualize the treatment. So Watson solutions suggest help to inform oncologist decisions based on a ton of information. I think somewhere the stats say that in order to stay relevant on all the information that's out there, doctors should read 5 hours of medical journals and clinical trials a day, which then when would they have time to treat patients? So the goal is that Watson can learn all this information, like I said, extremely fast, and then through a user interface, the doctors can pull up the relevant information per patient. WellPoint is, we're working with them to streamline pre-approvals for procedures. So right now, someone has to sift through and look, does this patient qualify for this procedure? Is this the correct path? That sort of thing. So Watson can use its information and the patient information to give the medical providers almost an instant response on whether it's pre-approved. And lastly, MD Anderson Cancer Center, and this is the project I'm working on, so I know a little bit more about this one. But the goal is to close the loop on clinical trials, patient care, and treatment development. So we have data loaded from, like it says, over 100,000 patients throughout current and past patients at MD Anderson, including thousands of clinical trials, publications, everything. But there's a lack of integration. So before, the doctor would have to go to all these different resources, look them all up, compile it, take a ton of time, and that's not possible for every single patient. So Watson can take all that background information, take the patient's characteristics, age, symptoms, past medical problems, family history, everything, sort through it all, and give the doctor. It pulls up clinical trials that they might be eligible for, and then also maybe it's one of the things. Clinical trials is a huge one, but one of two, maybe this person matches all of these clinical trials like requirements except for they need this test. It'll tell the doctor, okay, if you run this test, this patient might qualify for this clinical trial. It's individualizing medicine. And to summarize, this is kind of our Watson family, the way it works. There's the Watson Advisors, products based on Watson's core attributes and capabilities. Watson Solutions, which is where I fall, where we're working with the hospitals. The Cognitive Fabric, that's kind of referring to IBM research. So I briefly mentioned kind of some of the math principles that went into it, the algorithms. Watson Foundations, it provides the big data and analytic capabilities. It's more algorithms. And then the IBM Watson ecosystems is the developer cloud, Watson content store, talent hub, that sort of thing. There's actually, the Watson ecosystems is doing a competition right now. You can submit an idea. If you have an idea for an app that uses Watson, you can submit an idea, and if you're selected, they will help you implement your idea with your app idea with Watson. So that's one of the things going on there. So does anyone have any questions?
So is there any risk of Watson taking all of the jobs for doctors? I mean, as you're kind of making it sound like he can do everything they can. Well, I mean, obviously he can't perform surgery, but he can do, I mean, is there going to be, you won't go to a general physician anymore. You'll just type all your information into Watson and
I don't think so. You're still going to have research, medical personnel, obviously, people doing the research, people suggesting the clinical trials. I don't see it happening personally, because I think you're still going to need a trained medical professional to say, yes, that sounds accurate, no, that doesn't. In the stages that we're at right now, we're working with the doctors. They'll see, in Watson's interactive, so if it comes up with a list of suggestions, and maybe the top choice, there's some reason that doctor says, no, that's actually not a good choice, he can tell Watson, no, this is a bad choice, and this is why, and Watson will learn. So they're still in those stages, so you still, I think, need a doctor that can say, yes, that looks good, no, that doesn't.
You mentioned searching through and like assimilating hundreds of thousands of patient records. Are there concerns with privacy with patient health information?
Yes, it is huge, huge issue. I can't even tell you the number of training I had to do to even access the data, how much I had to fill out forms. It was almost like getting a security clearance to get access to the data, and they actually will not let us bring MD Anderson will not let us bring any of their patient information onto our own computers. If I want to run Watson, the computers are actually physically at their hospital, at their research center. To get access to them, I have to log on through servers and type in, I don't know how many passwords that I have to change every 60 days and all this stuff. And I can't, if I get fired, I can't even take the model that I built with no patient information and bring it to my computer. It all has to be remote accessed. So they're very, very strict about it.
Any other questions? All right. Oh, okay. Good.
How do all you had like the Watson family, how does everyone interact between all those teams, and like how big is each team, I guess?
That's a good question. The teams interact. It's almost hard to separate the teams. We interact so much. I mean, everyone's working together constantly. Sometimes it's the case where like you can't do something until someone else gets something done, but it's pretty dynamic. Everyone's working together. Everyone's jobs overlap. All of that. As to how big Watson is, right now, since we just got the new group, I want to say Watson Solution, like Watson, so IBM research is kind of separate. There's Watson jobs there, but that's research. That's the core algorithms. That's new development. The business side of things, we're less than 2,000. I think we're somewhere around 1,200, but we're growing. We're definitely hiring right now. If anyone's looking for a job, check that out. IBM in general is hiring, but Watson we're expanding. I do know the number that we're supposed to hire by the end of the year, and it's a lot. Hundreds by the end of the year.
That's some good information. All right, any other questions? Oh, we do.
So with the healthcare sort of applications, you said that Watson can suggest things that doctors should do. At what stage actually is that? Is that in hospitals at the moment, or is that just a thought of what it's going to be useful for?
No, it's in hospitals. As we develop and change things, so we have timelines and sprints for certain things the doctors want. And then as we get that done, it goes to the hospital. They test it out. They'll come back with feedback and say, yes, that worked. No, it didn't. We change it. Right now, I think we do 4 cancers. I think for the specific MD Anderson project that I'm on. It's only 4 cancers. But we call them sprints. They're it's like breaking the year into quarters, basically. But we're adding a new cancer each quarter. And we add them faster as we get more familiar with what they want.
Okay, great. Well, let's thank Samantha again. And we'll switch to our next speaker.